In September 1859, scientists observed the first confirmed powerful solar flare. The sun threw a large amount of radiation, energy, and plasma material into space. This was a massive and devastating disaster, but it happened 93 million miles away, so it probably wasn't such a big problem, right? Well, actually it was. A few hours after the flare was spotted, telegraph lines stopped working all over Europe and North America. Some of them sparked and caused fires. People realized that the sun was not only the source of light and warmth, but also danger. Scientists called that day the Carrington effect. The good news is that this happened in the middle of the 19th century and didn't cause serious problems for the planet. The bad news is that scientists are warning that in 2025, Earth will experience even more powerful solar storms caused by a coronal mass ejection. This is a giant cloud of plasma or charged gas. At one time, the sun can throw billions of tons of this material into space. Then, all this flies at high speed through space. Some of the material can reach our planet in 15 hours, the rest in a few days. During the journey, it captures and accelerates any charged particles encountered along the way, which increases its intensity and power. And then, this unstoppable array of energy crashes into our planet. It heats the upper layers of the atmosphere, increases its thickness, and disturbs the work of satellites. They slow down and lose altitude. Communication with satellites becomes unstable, GPS is buggy, data is poorly transmitted. Also, solar-charged gas penetrates into our power grids, transformer booths, and stations. It leads to massive failures that ruin the work of the entire technological chain. A powerful solar attack on several power plants can trigger a power outage in a large city. The internet, phones, social services, networks, nothing will work. We may lose connection with each other. Many large companies would go bankrupt, and the planet may face economic crises. These are big problems, but not the most serious ones. Electric plants serve boiler houses and water pumping stations. Solar storms could stop water from getting to our homes. You wouldn't be able to buy groceries in stores without cash. Of course, we can restore all this, but we'll have to live in the Iron Age for a while. But the worst thing is that a prolonged solar storm can suspend food production. For example, this year, a geomagnetic storm caused by solar storms shut down GPS satellites that are connected with modern tractors, so farmers couldn't work. What would happen if such storms happened every day for a year? We would probably start missing many items in supermarkets. Besides, maritime navigation also depends on satellites. Thanks to them, ships calculate the latitude and longitude of their location. If the satellites are damaged, ships may get lost in the ocean. Even whales get lost in the ocean during magnetic storms. Many birds navigate with the help of magnetic field during long flights to the south. So, not only people, but also animals may experience serious problems. Solar storms heat the upper layers of the Earth's atmosphere and thus make the air thicker. The movement of satellites slows down because of this air resistance. They lose altitude, and one of these satellites is Hubble. Yes, the very telescope that provides us with incredible pictures of space. Scientists say that it will fail much earlier because of solar attacks. You've probably heard on the news that solar activity has recently caused electromagnetic storms on Earth. But fortunately, it hasn't affected our lives in any way. The only problem was headaches, high pressure, and mood swings during those storms. It seems like an ordinary thing, but scientists don't have a consensus on this topic. No one has proven exactly how and why magnetic storms affect our condition. Yes, during storms, the planet's atmosphere becomes less dense, and perhaps this affects our blood pressure, like it happens when the weather changes. So people with cardiovascular system problems should be careful. But the effect on our nervous system, fortunately, is quite insignificant. It's possible that when people hear about a coming magnetic storm and feel unwell, they experience a placebo effect. But there's also good news. All these charged solar particles interact with atoms and molecules in Earth's atmosphere. This interaction leads to beautiful northern lights. It's good to spend some time away from your gadgets and look up at the sky sometimes. One of the biggest storms occurred on March 13, 1989. On March 10th, the Sun ejected a gigantic volume of coronal plasma. The amount of that material was the size of 36 Earths. The solar cloud was flying to us at 1,000,000 miles per hour, and a couple of days later, it crashed into our planet's magnetic field. The collision caused a geomagnetic superstorm. People watched some of the brightest and most beautiful auroras in history. The light show covered most of the planet, but after a beautiful performance, problems followed. The solar storm was so powerful that it went through the atmosphere and reached Earth's surface. First, it disrupted the operation of satellites and then damaged electrical networks. For example, it destroyed a transformer at a nuclear power plant in New Jersey. Energy companies in Canada went down because of systems overloading. As a result, about 6 million people in northeastern Canada lost electricity for 9 hours. This was the largest power outage caused by a geomagnetic storm. Yeah, there were more powerful storms in the mid-19th and early 20th centuries, but the planet wasn't covered by so many power grids at that time. More powerful storms may occur in 2025. The question is, will we be ready for them? Careful study of solar activity can help us prepare. If we know in advance about an upcoming storm, then scientists can switch off some systems and turn them on afterward, theoretically. If the activity of the sun increases every year, then we'll have to come up with new, innovative ways to protect ourselves. Who knows? Maybe scientists will cover all our electrical appliances and stations with a layer of special protective material. Anyway, we must do everything possible not to harm Earth's magnetic field, because if this shield disappears, the surface of our planet will resemble that of Mars. But what causes these solar storms, and why do they affect us so much? Okay, imagine a guy with a nice hairstyle who goes to bed. In the morning, his head is a complete mess. The magnetic fields of the sun are similar to this tousled hair. When the sun rotates, these fields burst, get tangled, stretch, and tear. At those moments, they release huge amounts of energy into space. This is not a problem for the sun, as the fields are restored during the process called magnetic reconnection. Such emissions can cause trouble for the planets in our system. When magnetic reconnection happens, several phenomena can follow. One of them you've already heard about. It's a coronal mass ejection. But there's another terrible thing that the sun does, and it's called solar flare. Imagine a bright burst of solar radiation containing electromagnetic waves, X-rays, radiation, and visible and ultraviolet light. During flares, the sun releases an enormous amount of this destructive energy, and it spreads through space at the speed of light. It takes 8 minutes for this explosive wave to reach our planet. Fortunately, we don't get much damage from these flares because Earth's magnetic field and atmosphere protect us. Strong flares can disrupt radio waves in the upper atmosphere and affect the operation of satellites, but it's nothing critical. Another solar phenomenon is called a radiation storm. These are accelerated electrons and protons that move at a speed slightly less than the speed of light. Thanks to Earth's magnetic field, radiation storms don't harm our planet too much, but they pose a danger to astronauts and satellites. These particles can penetrate human tissues and lead to serious health problems in the way radiation does, but only if you're in space or flying a plane in the upper atmosphere.
It was September 2nd, 1859. People all over Europe and North America woke up at night, confused and still tired. They were sure it was already morning. It was so bright outside. But when they looked out of their windows, they discovered it wasn't sunlight. The skies were lit by countless intense auroras, red, green, and purple. They were so brilliant, one could read a book as easily as in the afternoon. Auroras appeared even in the regions where they had never been witnessed before, like Cuba, the Bahamas, Jamaica, and Hawaii. Cool visual effects weren't the only thing that both mesmerized and horrified people. The most high-tech stuff at that time, telegraph wires, shorted out throughout Europe and the US. Sparks were flying from equipment, and many human operators got electric shocks. Papers and telegraph offices burst into flames. All the machines were immediately disconnected from their batteries, and still, they mysteriously kept sending broken messages. Fires, ignited by short circuits, spread over large areas. Colorful lights kept dancing overhead. All this caused panic and total confusion. Earth's inhabitants had never seen or experienced anything like that before. At that time, very few people knew that the sun was to blame for the chaos. One of them was English astronomer Richard Carrington. At about 11 a.m. on September 1st, the man was standing by a telescope in his private observatory. He was watching sunspots on the surface of the sun. Suddenly, two patches of intense white light broke out. They looked as bright as direct sunlight. At that moment, the astronomer didn't know what a terrible commotion these flares would cause. Later, it became clear that the sun had produced an epic geomagnetic storm and unleashed it at our planet's protective layer. Wave after wave of charged particles slammed into Earth's atmosphere. The planet's magnetic field wasn't powerful enough to stop them. It gave way, and the storm hit Earth, causing havoc. The phenomenon got the name of the Carrington event. So far, it's been the worst solar storm ever recorded. Good thing it happened when people didn't have advanced technologies and weren't that vulnerable to the sun's geomagnetic fury. The 1859 solar storm was 3 times more powerful than the one that happened on March 13, 1989. 3 days before it began, astronomers watched a massive eruption on the sun's surface. Within a couple of minutes, a billion-ton cloud of gas was hurled away from the star. It rushed straight toward our planet at a speed of millions of miles per hour. On Monday the 12th, the huge mass of solar plasma reached Earth's magnetic field. This storm was so fierce, it lit spectacular auroras and created underground electric currents beneath North America. These currents must have found some weaknesses in the power grid of Quebec, Canada. In less than 3 minutes, the entire city lost power. Millions of people found themselves in pitch-black streets, dark buildings, and stuck elevators. They woke up in freezing cold homes, unable to cook breakfast. The following 12-hour blackout closed businesses, airports, and schools. The Montreal Metro was also shut. In the US, hundreds of power grids started to have problems minutes after the storm hit Earth's surface. Luckily, none of these issues led to a blackout. The storm was severe enough to disrupt satellite communication systems and radio signals. Some space satellites tumbled out of control for a few hours. Lots of them had mysterious problems that went away as soon as the storm began to subside. No newspaper mentioned it, but in 2012, Earth had a close shave after narrowly missing an extreme solar storm, the most intense in the past 150 years. On July 23rd, astronomers at Space Weather Prediction Center in Colorado spotted 2 clouds of energetic particles. They erupted from the sun's surface and barreled into space. Just 19 hours later, these clouds zoomed past the spot our planet had just left. If the solar eruption had happened several days earlier, Earth would have ended up in the line of fire. So, what if a solar storm as powerful as the iconic Carrington event happened nowadays? How much more harm would it cause? Would our life get back on track after such a disaster? Before you learn the answers to these questions, let's figure out what a solar storm is. The sun is a gigantic, constantly changing ball of molten gases. Every once in a while, it spews out bursts of energy, solar flares. They often go hand in hand with something called coronal mass ejections. Those are giant bubbles of ionized gas that can speed up to more than 600 miles per second. The most powerful volcanic eruptions pale in comparison with solar flares that release 10 million times more energy. Within a few minutes, one solar flare can give out billions of tons of charged particles. Solar flares are also insanely hot, with the temperatures reaching several million degrees Fahrenheit. Astronomers believe that such bursts of solar radiation happen when the sun's magnetic field gets twisted in some regions. At one moment, all the pent-up energy is released. The star sends out light and particles, mostly electrons and protons. Most solar flares last for minutes, but some continue for hours. Scientists classify solar flares depending on how brightly they shine in X-rays. You aren't likely to notice the tiniest flares if you don't have special equipment. Medium solar flares lead to fleeting radio blackouts at the poles, but nothing too serious. It's X-class flares people should worry about. They cause the strongest and longest-lasting solar storms. When people think about danger coming from space, most of them imagine an approaching asteroid, like the one that wiped out the dinosaurs. But apparently, we should be much more worried about our good old sun. A super strong solar storm heading toward Earth won't happen at once. First, there will be high-energy sunlight, mostly ultraviolet rays and X-rays. They will ionize our planet's upper atmosphere and mess up radio communication. After that, a radiation storm will hit Earth. And finally, several days later, a colossal cloud of charged solar particles will reach our atmosphere. The particles will interact with the planet's magnetic field and wreak havoc all over the world. If an intense solar storm happened these days, it would start by disrupting GPS and knocking out satellites. If any astronauts were spacewalking at that moment, they would have a mere minutes after the first flash of light to find shelter. Their spacecraft would likely be properly shielded and safe enough. The main challenge would be to get inside in time. After that, the storm will proceed to interfere with satellite communications. That's why tons of your daily activities, from calling your friends to paying with your credit card, would be at risk. But one of the worst consequences would be connected with power grids. Power surges caused by the particles coming from the sun would damage giant transformers. Those take ages to replace, especially if hundreds or even thousands get wrecked. In some places, a failure of one power grid would make others collapse as well, creating a domino-like reaction. Picture living without electricity for a day, a month, a year. No light, no computers, no phones, water supply systems out of order, no food in supermarkets. Plus, without electricity, it would be next to impossible to reboot the already failed power grids. A powerful solar storm would cost people $1 trillion to $2 trillion, and that's just during the first year after it happens. It would take the world another 4 to 10 years to recover. The damage to all kinds of satellites alone would reach $70 billion. Under majestic auroras, people would have to get used to a new, dramatically different lifestyle. No doubt, we'd have some kind of warning. Modern equipment all over the world and in space doesn't stop watching the sun even for a second. Once a bad solar storm happens, people would have some time to prepare, between several hours and a couple of days. And if transformers are taken offline in time, the consequences won't be so dramatic. Now, the following news might sound scary. There are also super flares. In comparison to them, our sun's bursts of radiation are small potatoes. Super flares mostly occur in young and active stars. In 2016, astronomers saw such a phenomenon. A star 1,500 light-years away from Earth produced a flare that was 10 billion times more powerful than any of those that burst from our sun. It doesn't mean we're safe here on Earth. Even our middle-aged sun knows how to produce super flares, but while young stars can have them once a week or even more often, for the sun, it's once in a few thousand years. And still, if people don't figure out how to protect the planet, just one super flare can shred our ozone layer and wipe out life on Earth.
From where we stand, the sun seems so calm and peaceful, but like humans, and basically the whole living world, the sun has its own phases when it's more or less active. It's just that the consequences are way bigger and more chaotic when the sun becomes hyperactive. Let's zoom in to see what's happening up there. So one of the ways we measure the activity of our star is by counting sunspots on its surface. Sunspots are dark patches that form when the sun's magnetic field gets all tangled up. It's simple. The more sunspots, the more active our sun is. And it seems the sun has been partying like crazy recently. The number of sunspots scientists have seen is the highest for nearly 21 years. In June, 163 sunspots appeared on the sun's surface. The last time we had so many dark patches across the sun was in September 2002, when there were 187 of them. Uh-oh. It seems this chaotic party is getting closer to its peak. And that's something we call solar maximum. How does all this even happen? The sun's magnetic field is strong and organized at some point. But as we said, sometimes comes the time when it kinda ends up tangled. Sort of like a ball of rubber bands that are wound together very tightly. This also means plasma is rising from the surface, forming loops, and causing a mess in the shape of solar flares and something we call coronal mass ejections, CME. That's when plasma in the sun's upper atmosphere, called the corona, goes crazy and bursts really strong. Then at some point this ball snaps and completely flips and turns the South Pole into the North Pole and vice versa. All this happens every 11 years or so. So when the sun comes into this phase when it becomes very active, it shoots out hot blobs of plasma, gets big dark spots as large as planets, and releases powerful eruptions of energy and radiation. Something fascinating happens when the sun becomes more active. A thing called plasma waterfall or polar crown prominence, PCP. It's like a mini eruption that starts on the sun, and it seems like it tries to get away, but then the sun's magnetic field pulls it back before it can escape into space. And this plasma waterfall's really spectacular. It goes up to 62,000 miles above the surface. It's like you stack 8 Earths on top of each other. Then there's something called a polar vortex. It's like a gigantic halo of plasma that rotates around the sun's north pole really fast. This vortex happens when a large tentacle of plasma snaps apart and falls back toward the surface, similar to how a plasma waterfall forms. Scientists don't know why this plasma stays above the sun's surface for so long. And one of the cool examples of CMEs was a giant one in the shape of a butterfly in March this year. It got such an unusual shape because it exploded on the side of the sun we couldn't see, so it was impossible to fully measure how strong it was. Fortunately, that one didn't explode in our direction, but it might have hit Mercury a little bit. And it's possible it knocked off some dust and gas since Mercury has a weak magnetic field. All this sounds cool in theory, but it's not such good news for us. Because of all this, we might experience more intense solar storms that can, again, lead to geomagnetic storms on Earth. And these don't just sound alarming, they indeed are. They create chaos and disrupt the magnetic field of our planet. Geomagnetic storms can create beautiful northern lights, true. But we'd all rather enjoy such beauties as the aurora borealis in regular conditions, or just watch a good old sunset above the ocean. It's not that every solar storm will necessarily hit Earth, even if there are more of them. To reach our planet, they must be pointed in the right direction at the right moment. But if that happens, the storm can ionize the upper atmosphere, and bye-bye our communications. It can cause temporary blackouts for systems such as GPS and radio. It isn't necessarily a big problem on its own, but it can be very dangerous if it happens at the wrong time, like during a tsunami or an earthquake. The storms can also damage electrical infrastructure, like rail lines and power grids. If you're on a plane at that time, you might be exposed to higher levels of radiation. It's still not clear how dangerous that will be for you, but it can be a serious problem for astronauts in space. When solar storms mess with the magnetic field, this can affect the migrations of some animals, such as sea turtles, whales, and birds. Since things in the animal kingdom mostly work in the natural order, who knows how these animals go through or even survive such changes? And when the sun is at a maximum of its activity, satellites in space are in trouble too. We have more satellites in space than ever before. And when the upper atmosphere becomes denser because of all these changes, this can push satellites in different directions. They might crash into one another, or some can even fall back to Earth, which again is only cool in movies with superheroes who can relatively easily deal with this stuff. Hopefully, we'll avoid a massive solar storm like the Carrington event. The story was similar. In August 1859, astronomers across the globe watched how the number of sunspots was getting bigger and bigger. A man named Richard Carrington was among them. At the beginning of September, he was sketching the sunspots when, out of a sudden, he was blinded by a flash of light. It lasted around 5 minutes, but it was spectacular. He later described it as a white light flare. It was a very strong coronal mass ejection, CME, and in only 17.6 hours, this storm crossed the long way between the sun and our home planet. 90 million miles, and unleashed its force on us, even though this usually takes days. And when this storm started, telegraph machines across the world sparked. Operators got electric shocks, and paper even caught fire. People were really scared and confused because they had never seen such bright skies before. Some even thought it was the end of the world. The next day, telegraph workers still couldn't work properly because Earth's atmosphere was still charged. They even managed to send messages using the auroral current instead of regular electricity. But it brought something incredible, 2 stunning auroras in the sky. People in Hawaii and Cuba could see beautiful northern lights, while those as far north as Chile could see the southern lights. It's all slowly but steadily escalating. Take solar flares, for example. These are powerful bursts of energy from the sun. In 2022, there were 5 times more of these flares compared to the previous year. Plus, the strongest ones, X-class flares, have been getting stronger and more common than before, too. And this might be way more extreme than anyone thought. Plus, it's likely to start a little bit earlier than we predicted. Scientists first thought the peak would happen in 2025, but it seems it could even occur by the end of 2023. We can't completely protect ourselves if a solar storm hits us directly, but we can still do some things like ground planes, adjust the paths of satellites in space, and try to make sure vulnerable infrastructure stays safe. To do all this, we need better solar weather forecasts to help us get ready for the worst. All this might sound very bad at first, but don't worry, solar flares won't destroy our planet. They do send charged solar material toward us at pretty high speeds, but it's not like we're completely doomed if these things hit us. Our planet won't leave us unprotected. We still have the atmosphere and magnetic field that keep us relatively safe. Our thick atmosphere is like a shield that blocks radiation that might harm us. So these solar flares can mostly affect technology, but they won't destroy Earth. I guess we have our own superheroes after all.
A recent study has involved almost 200 huge stars that are reaching the end of their lives. It has given scientists more precise information about how the sun will one day end. It turns out that the sun will be about 200 to 300 times bigger than it is now by the time its game is over. For starters, let's begin with some basic information about star sizes. Giant ones reach this stage because they've run out of nuclear fuel and are no longer burning hydrogen in their core. Eventually, the core gets hot enough to trigger the next stage of fusion, which is helium burning. All the stars that were surveyed in this new study were either in this hydrogen shell burning or helium core burning phase. Even though giant and supergiant stars only make up less than 5% of all stars, or at least that we know of, they're actually really visible from a distance because they're so bright. In fact, according to scientists, about a third of all the stars you can see outside on a dark, moonless night are giant or supergiant stars. This study will eventually give astronomers really useful info about massive stars. They'll be able to figure out their size and temperature, no matter where they are or their evolutionary stage. This means they can see a star's true color and use that to find out its radius. Pretty cool, right? It does raise the question, what will our sun be like when it gets old and grumpy? To put it simply, it will expand when it starts burning its hydrogen shell, but then shrink a bit during its helium core burning phase. After a few 100 million years, it'll end up as a giant star, about 200 to 300 times its current size. Eventually, the sun will expand so much that it will simply evaporate. So, what will happen after the sun fades away? Scientists actually have some predictions about what will go down, even though we won't be around to see it. They're pretty sure the sun will turn into a planetary nebula. These planetary nebulae are chunks of gas and dust in space that come from a star that is fading away. They got their name because they looked like planets to people using telescopes back in the 18th century, even though we now know they have nothing to do with actual planets. And here's the crazy thing. Astronomers have found out they can use the level of brightness of these planetary nebulae to calculate their distance from us. In 2018, Scientists also found out that the Sun is the smallest a star can be to still be able to produce a visible nebula. Any smaller and it would not be visible. Stars that are up to 3 times more massive than the Sun will produce brighter nebulae. The Sun is currently 4.6 billion years old, but it's estimated to have another 10 billion years until its end. The Sun is also getting brighter with each year. It doesn't seem like a lot now, but it's actually going to cause some big problems for Earth. In about a billion years, the Sun will be too bright for life on Earth to survive. Our oceans will evaporate, and it will be too hot for water to form again. So unless we find a way to escape from this planet, humanity only has about a billion years left. Will Earth still be around by the time the Sun turns to dust? It's hard to know for sure the exact timeline. But even before that happens, Earth will most likely be scorched and lifeless, with no atmosphere or oceans left. It's not clear how close the Sun's outer layers will get to Earth, but if they get too close, it could cause Earth to spiral into the Sun and disappear altogether. Even if our planet does somehow manage to survive the Sun's giant phase, it will be orbiting a hot white dwarf, or a star that has run out of its fuel. In that distant future, the Sun will be barely larger than our planet. Eventually, the Sun will cool and dim completely. It'll move to another stage called a black dwarf. It will cause Earth's orbit to loosen up, and our planet will spiral into the fated Sun. But interestingly, the Sun doesn't get the final say in what happens to Earth. Gravity keeps planets in orbit, but it also attracts them to each other, which can cause their orbits to flex and drift. This could lead to the solar system destabilizing and ejecting planets, including Earth. Basically, a lot might happen in the next 5 billion years before the Sun becomes a red giant. There's also another scenario. While most stars stay far away from our solar system, there's a chance that one could come closer in the next billion years. Even a small star or black hole could mess up the orbit of our planet if it gets too close. But don't worry too much, the odds of that happening are low because of the amount of space between stars. Our Sun is a solitary star, so there's little to no chance we'll be able to catch a ride with another one nearby. However, many stars in our universe have companions. Among these stars is Castor, a stunning system that comprises 6 stars and is one of the brightest objects in the night sky. Although humans have been admiring Castor for ages, they were not aware of its true nature until the invention of telescopes and spectroscopes. Even with the help of a small telescope, it's evident that Castor is composed of 2 primary stars, Castor A and Ba, that revolve around each other. These stars are larger than the Sun and need 467 years to complete one orbit. In total, Castor is composed of 6 different stars. The biggest one, called Castor AA, is roughly 2 times larger than the Sun, while the smallest has about 0.5 of the Sun's mass. If humans want to survive the next billions of years, we might need to set up camp somewhere else in the universe. It may seem like something out of a sci-fi movie, but it could be our reality one day. Thankfully, NASA is already looking at some options. They've discovered 2 new planets, TOI 700e and TOI 700d. That might be new hotspots for us humans. TOI 700e is the optimistic zone, which means it could have water and even an atmosphere. TOI 700d is in the conservative habitable zone. So, scientists aren't too sure about it yet, but hey, we'll take what we can get. But hold on, before you start packing your bags, there's a little problem. How do we get there? It took John Glenn months of preparation just to circle Earth 3 times. So we might need to start working on our astronaut training. Well, at least we have some options for our future intergalactic vacation plans. Wouldn't it be nice if we could time travel so we could see what our solar system will look like in billions of years? An American physicist named Ron Mallett has proposed one interesting theory for time travel. It uses light, a resource that is abundant in the universe. His idea involves using a rotating cylinder of light, which could transport an object in both space and time, similar to how a bubble moves in a swirling liquid. Mallett suggests that a cylinder of the right shape could allow for travel to the past and the future. To test his theory, he has been trying to secure funding for an experiment. However, some scientists consider Mallett's theory to be impossible and unnecessary to test. We might also be able to travel through time if we move fast enough. According to Einstein, the way we experience time can change depending on how fast we're moving. If we go really fast, time slows down. For example, astronauts in space age a tiny bit more slowly than people on Earth. This is important for things like GPS, which would be incorrect without special adjustments because of how time is affected.
Well, it turns out black holes might not be as elusive as we once thought. They might be hiding within stars. In this case, the extra mass of some of these space lanterns could explain weird gravitational effects in the universe. Previously, dark matter was the cause of these phenomena. The black holes I'm talking about might be those itty-bitty ones that appeared at the dawn of time when the universe was just a baby. And they may still be lurking in the hearts of giant stars. A team of scientists say the idea might be quite plausible. Astronomers could detect such trapped black holes by the vibrations they produce on their star's surfaces. And if there are many of them out there in the cosmos, they might function as the very dark matter that holds the universe together. Almost any black hole was once a massive star that collapsed in on itself and became incredibly dense. Black holes have immense gravitational pull. Even light can't escape their clutches. People often think that black holes work like vacuums, pulling space inside. But that's not the case. Black holes can only swallow stuff that is extremely close, usually space objects venturing into their event horizon. That's a black hole's point of no return. Once you cross this border, there's no escape. In 1971, renowned physicist Stephen Hawking suggested another origin of black holes. If we took the thick soup of particles that appeared moments after the Big Bang and the birth of the universe, we'd be bound to find some spots dense enough to collapse and create black holes. Such holes, which got the name of primordial black holes, could range in size from microscopic to gigantic. If they were pervasive and numerous enough, primordial black holes could act as dark matter, knitting the cosmos together with their enormous gravity. And dark matter is believed to make up 85% of all the matter in the universe. So what's the matter? Astronomers have been searching for primordial holes by looking for flashes that would occur when they pass in front of distant bright objects, magnifying their light like a lens. But they haven't spotted even one yet. On the other hand, if a primordial black hole was tiny enough, with a mass like that of an asteroid and a diameter as minuscule as a hydrogen atom, the flashes wouldn't be bright enough to be detected by such surveys. Then the team, researching the phenomenon of primordial black holes, decided to consider the consequences of a universe where dark matter was made entirely out of tiny black holes. They concluded that one of such teensy holes could be dashing through the solar system at any given time. Some might occasionally get trapped within gas clouds, giving birth to new stars, ending up in their centers. The next step of the researchers was to build a model of a black hole existing in the very core of a star, where hydrogen atoms undergo fusion and produce light and heat. At first, they didn't see anything unusual. Even a super-dense stellar core is mostly empty space, and it wouldn't be easy for a microscopic black hole to find matter to consume there. That's why its growth would be incredibly slow. It could take longer than the lifetime of the universe for this tiny hole to eat a star. But what if a larger hole, as massive as the dwarf planet Pluto or asteroid Ceres, appeared at the center of a star? Then it would get bigger in a matter of a few 100 million years. The material would keep spiraling into the black hole, creating a disk that would heat up because of friction, emitting radiation. Once the black hole grew to the size of Earth, it would start emitting even more radiation, shining extremely brightly. It would also be churning up the star's core, and the star itself would turn into a black hole-powered rather than a fusion-powered object. Such entities were dubbed Hawking stars. To cool off, the exterior of a Hawking star would form a red giant. That's what our Sun is likely to turn into as it gets older. But a red giant star with a primordial black hole at its center would be cooler than the stars that have reached this stage through regular means. Such stars are known as red stragglers. To find out whether they indeed host a black hole, astronomers might need to tune into the frequencies at which stars vibrate. Since a Hawking star would mostly affect the interior of the star rather than its topmost layers, the star would thrum with a certain combination of frequencies. The waves created in the process could be detected in a way the star's light would pulse and throb. So, all scientists need to do now is study the already known red stragglers and figure out whether any of them show the characteristic vibrations of a black hole. Now, should we worry about the Sun? Since our star hasn't reached its red giant stage yet, we can't know whether it'll turn into a cool red straggler. What we know, though, is that our star might contain those tiny black holes that formed in the Big Bang. But now, we have no means to check whether they're indeed there. Currently, our star is around the midpoint of its existence, middle age. It creates energy non-stop by fusing hydrogen atoms within its core. Once it runs out of hydrogen in its core, it will enter its red giant phase and begin to collapse. It'll happen in about 5 billion years, don't hold your breath, and the phase itself will last for 1 billion years or so before our star depletes its fusible materials and loses its outer layers. It will leave behind a tiny white dwarf star half as massive as the Sun and around the size of our planet. In some cases, when the gravitational collapse of a star's core is complete, the star remnants turn into a black hole. But that's not the fate awaiting our Sun. You see, our star just doesn't have what it takes to become a black hole. It's not heavy enough. There are a few conditions that can affect whether a star can turn into a black hole, including its composition, rotation, and the processes that lead to its evolution. But the main requirement is still the right mass. Stars with 20 to 25 times the mass of the Sun can potentially experience the gravitational collapse needed to form black holes. In other words, the Sun is simply too small to form a black hole. But what would happen to us if it did? You might assume that if the Sun turned into a black hole, our planet would be doomed to be pulled into it. But do you remember the basics? Black holes aren't giant space vacuum cleaners, just sitting there and waiting for a new planet or star to get their hands on. Mwah. But black holes don't have enough gravitational force beyond that created by their incredible mass. And if the Sun were to turn into a black hole, which will not happen, this hole would still have the same mass as our former star, and Earth's orbit around this newly formed black hole wouldn't change. But all other things would change dramatically. The Sun, which is currently around 432,000 miles in radius, would shrink to a mere 1.9 miles in radius. But you wouldn't be concerned with the absence of the bright yellow sphere in the sky, since you have many more pressing issues on your hands. Our planet's main heat source would be gone, leaving us frozen in the dark. Without this source of energy, photosynthesis would immediately stop, disrupting entire food chains. Eventually, all life on Earth would be extinguished. But rest assured, our hard, barren rock of a planet would continue in its orbit. Oh well.
The Sun is getting ready to flip as its magnetic poles are reversing. Similar to Earth, the Sun has a magnetic north and a magnetic south. But unlike Earth, the reversing process of the Sun's poles is more frequent and easier to predict. The next flipping is expected to take place this year between April and August. As apocalyptic as it might sound, you don't have to worry. If you're around 30, you've already experienced this phenomenon more than once as the Sun flips every 11 years. You probably didn't notice any changes back then because this process doesn't impact Earth's life so much. But this time, things might be a little different. On Earth, ocean currents are movements that play a crucial role in influencing both climate and weather by distributing heat from the equator to the poles. On the Sun, these currents are more like an ocean of plasma, but they not only transport heat but also carry electromagnetic energy. That happens because the Sun is a huge ball of hot and ionized gases that keep flowing inside its core. By fusing together hydrogen atoms and forming helium, our star releases a massive amount of energy, leading to these very heavy flowing electric currents. And whenever you have currents, you have magnetic fields. It's easier to understand if you think of that classic experiment with a wire and a nail that you probably conducted in elementary school. When electricity flows through a wire, it creates a magnetic field around the wire. So when you connect a wire to a battery and wrap it around a nail, the nail becomes a magnet. This is similar to how electric currents create magnetic fields on the Sun. This whole process, with the help of which the Sun generates its magnetic field, is called a dynamo. We can't observe it directly, but we can see its effects on the Sun's surface. When plasma and magnetism flows become unstable and intense, they manifest as sunspots. You know, those dark areas on the Sun's surface? Much about how the dynamo works remains a mystery. But scientists have learned something important after observing these sunspots for centuries. The dynamo process follows a pattern. About every decade, it reorganizes itself. The Sun's polar magnetic fields get weakened, eventually reaching zero, and then they return, but with the opposite polarity. Back in the 50s, researchers figured out that when sunspots start to ramp up and become more intense, it means the poles are gearing up for a reversal. And over the past few years, solar activity has been off the charts. We're talking about more solar flares, more electromagnetic radiation bursts, and more plasma blobs being ejected into space. It's like we're sitting in the front row at the solar system's most epic fireworks display. In fact, the Sun hasn't been this lively in probably 2 decades. Right now, experts think the polar fields are almost in sync and steadily weakening, inching closer and closer to zero. But we haven't reached the point of reversal yet. Although it might sound like the Sun flips its magnetic poles like clockwork every 11 years, the truth is that it's not as neat as it seems. This path can be bumpy, and some aspects of the phenomenon are still very hard to predict. Take the last solar cycle, for example. The Northern Hemisphere started its magnetic flip back in early June 2012. But then it kinda hit a snag and lingered around the neutral point until late 2014. Meanwhile, in the Southern Hemisphere, things were smoother, with the polarity switching over in mid-2013. This time around, the Sun is actually playing nice. Things seem to be running way smoother this cycle, with the poles transitioning more evenly. But here's the thing, reversal processes are never the same. That's what makes this phenomenon so interesting to observe. But at the same time, it's hard to predict how it'll affect us down here. Here on Earth, we don't have to worry too much about those intense sun explosions happening 93 million miles away. But if, and I emphasize if, a solar storm were to reach our planet, the main threat it would bring would probably be the disruption of communication satellites in space. However, things might be different in this cycle reversal happening in 2024 because the number of satellites has skyrocketed in recent years. For example, Elon Musk's Starlink system alone involves more than 4,000 of them. All these satellites, along with communication and GPS satellites, could be impacted or even destroyed by a powerful solar storm. Although the chances of a powerful solar storm hitting Earth are low, it's not impossible. Back in 1859, during the Carrington event, a storm occurred near the peak of the solar cycle, causing currents to surge through telegraph lines, sparking fires and disrupting messages worldwide. Earth fell silent as telegraph communications failed. Just imagine what a solar storm could do to our vast number of satellites today. It could affect everything we rely on daily, from space-based communication and navigation to weather forecasting services. The ground-level power distribution could also be affected. You can forget about watching YouTube or Brightside, because if such an event occurred today, it would cause an internet apocalypse. sending countless people and businesses offline. There's a prediction that says that if a Carrington-class event happened today, it would result in damages ranging from $0.6 to $2.6 trillion. And I'm talking about the United States alone. Fortunately for us, solar storms as intense as the Carrington event happen only once every 500 years or so. Bad news for communication satellites, but great news for aurora watchers. During the Carrington event, dazzling auroras borealis lit up the sky as polar light shows stretched far beyond their usual ranges. The northern lights were spotted as far south as Cuba and Honolulu, Hawaii, while the southern lights were seen as far north as Santiago, Chile. For many people around the world, this was their first glimpse of the aurora, leaving them obsessed with the unusually bright skies. Some of them thought it was the end of the world, while others began their day early, thinking the sun had risen after hearing birds chirping and seeing the bright skies. Today, we know there's nothing strange about it, considering that the appearance of auroras at lower altitudes is one of the expected effects of the sun's magnetic pole reversal. Typically, these dazzling phenomena are found between 60 and 75 degrees latitude, but during the last magnetic pole reversal in 2013, intense auroras were observed below 50 degrees. Eyewitnesses describe these auroras as blood or deep crimson red, shining so brightly that you could read a newspaper in their light. It's important to study this phenomenon and not to fear it. The inversion of the magnetic poles on the sun is actually a great opportunity for scientists to better understand how our star works. Since many pieces are still missing in the whole dynamo situation, we're still not very good at predicting why some solar cycles are more intense than others, or when exactly a coronal mass ejection will erupt. But being able to predict that is becoming more and more necessary as we venture ourselves into space. The more people are out there beyond Earth, the more exposed they are to these strong solar storms. That's why the scientific community wants to know more precisely when a solar storm can cause damage to spacecraft and space stations. Plus, it would help meteorologists make progress in predicting weather, not only on Earth, but also in space. The whole point is to make space travel safer as the interest in crewed missions to the Moon and Mars grows every year. Another reason why it's important to learn more about the Sun's pole inversion is to better understand how the mysterious interior of the Sun works. That could actually help us figure out the aspects of other stars in the universe and maybe get closer to answering the ultimate question: why are we here? Black holes are massive, the densest objects in the universe. They have such a great mass that their gravitational pull doesn't let anything, even light, escape their clutches. But in this terrifying world of black holes, there are monsters that are in a league of their own. Recently, astronomers discovered a black hole that is 33 billion times as heavy as our Sun. This space giant sits at the center of a supergiant elliptical galaxy called Abell 1201, which is located 2.7 billion light-years away from our planet. This black hole is so large it was given a rare designation, an ultramassive black hole. No wonder. It's more than 8,000 times heavier than the supermassive black hole at the center of our home Milky Way galaxy. This ultramassive black hole was the first one to be discovered with the help of gravitational lensing. This method is based on the fact that very massive objects such as galaxies bend the light from a more distant object, magnifying it. A great thing about this method of research is that it allows astronomers to study inactive black holes too. It could help us detect loads of new black holes beyond our universe. That's what the area surrounding our galaxy is called. Probably it would help us find some exotic objects we've never seen before. Now, let's speak about another awesome instrument that efficiently helps us explore space, the James Webb Space Telescope. When it stares at young galaxies, which would look like mere red specks to you, it sees an astonishing number of cyclones churning at their centers. Those are black holes. Interestingly, giant black holes were believed to be big players in early cosmic history. But James Webb regularly finds an unexpected number of these beasts. For example, using the telescope, astronomers have detected a supermassive black hole from when our universe was less than 600 million years old. In universe terms, it's just a baby. This is the most distant actively feeding supermassive black hole ever observed. It's located at the heart of its host galaxy called CEERS 1019. The black hole is surprisingly small and not massive at all. It's actually one of the smallest found in the early universe. It's equal to approximately 9 million suns. It might sound like a lot, but in reality, supermassive black holes tend to grow to billions of times the mass of our star. There's another unusual thing about this find, and scientists are having a hard time trying to explain it. You see, it's supposed to take way longer than 600 million years for a supermassive black hole to grow to its full potential. The development happens when a black hole either feasts on surrounding matter or merges with a larger black hole. Even black holes similar to the one at the center of our Milky Way galaxy, which is almost 4.3 million times the mass of our Sun, are supposed to be seen in the more recent universe. Actually, scientists have long suspected that supermassive black holes probably existed in the early universe. But this theory has been proven only thanks to the JWST and its infrared eye. It's shown that the black hole CEERS 1019 is actively munching on all the matter it can lay its hands on. Such feeding black holes are usually surrounded by swirls of gas and dust, falling inside them, called accretion disks. The gravitational force of a black hole heats this matter, and it makes the disk shine. And that's not all. Extra strong magnetic fields produced in this process channel the matter to the poles of the black hole. From time to time, this matter is released into space in twin, powerful jets. They move at a speed that is close to the speed of light, which generates incredibly bright light. Astronomers were watching the galaxy hosting the unusual old black hole as part of the Cosmic Evolution early release SINCE survey. They saw the galaxy as it was when our 13.8 billion-year-old universe was just 570 million years old. Besides the super old black hole, scientists spotted two other ones. Those probably appeared 1 and 1.1 billion years after the Big Bang. They also discovered 11 ancient galaxies that existed between 470 and 675 million years after the beginning of cosmic history. Now, how about having a look at the biggest black holes astronomers have found so far and finding out what would happen to Earth if one of them was to enter the solar system? NGC 6166 is a monster that has grown to have a mass of 30 billion solar masses. It's an elliptical galaxy that has an active nucleus at the center. It's also one of the most luminous sources of X-rays. The galaxy's supermassive black hole powers two symmetric radio jets in the opposite direction, which is the result of the infall of gas into its center. Another peculiar thing about NGC 6166 is that it shows a blue shift, which means it's moving towards us. Is it time to pack up and move out of our solar system? The next supermassive black hole is located in the constellation of Draco, approximately 10.4 gigalight-years from us. The mass of this supergiant is more than 30 billion solar masses. Besides being incredibly massive, the black hole is also really big. If it replaced our Sun, the diameter of this hole would extend to the orbit of Pluto. The next black hole is one of the most interesting on our list. It has a mass of 40 billion solar masses and is actually a blazar. It's the most energetic of all quasars, super bright distant objects. The blazar's luminosity is 300 trillion times that of the Sun, and more than 25,000 times as great as the luminosity of all 100 to 400 billion stars of the Milky Way galaxy combined. But since the distance to this quasar is about 12.1 billion light-years, we can't see it directly. But we know that the central black hole of the quasar consumes huge amounts of matter. About 4,000 solar masses of material every year. IC 1101 is a supergiant elliptical galaxy. It's the most massive known galaxy so far. Since this galaxy is elliptical, it isn't filled with gas. That's why the star formation in that region is very low. As for the black hole at the center of this galaxy, it lies in the mass range of 40 to 100 billion solar masses and emits clear radio signals. But wait for this champion. Astronomers have discovered a gravitational space wonder that has grown to really unimaginable proportions. The black hole I'm talking about is TON 618, and it's a mind-boggling 66 billion solar masses. Yep, we've got another ultramassive black hole here. Imagine gathering all the stars in our home Milky Way galaxy and squishing the matter they're made of into one black hole. And it still won't be enough to create a TON 618. If this monster of a black hole replaced the Sun, its radius would be more than 40 times the size of Neptune's orbit. You know that black holes are incredibly dense, but it doesn't mean they're some kind of space predators roaming galaxies and munching on everything they come across. TON 618, for example, still has a whole galaxy filled with stars and other stuff happily orbiting it without getting pulled inside. So the perception of black holes as giant vacuum cleaners is wrong. In reality, it's incredibly hard to grow a black hole. Try and you'll see. And now, what if a supermassive black hole, like the one that dwells at the center of our home Milky Way galaxy, moved a bit closer to our solar system? The answer is simple. We'd be doomed. The distance between this huge thing and Earth would be several dozens of light years, and still, it would wreak total havoc on our planet. Earth, along with other objects making up the solar system, would be tugged into the black hole's orbit and doomed to spin around it for eternity. But you can relax and breathe out. Such massive black holes stay away from us at the moment.
On July 23, 2024, Europe's Solar Orbiter spacecraft observed a super-powerful solar flare erupting from the far side of the Sun. This flare wasn't the most extreme ever recorded, but still, we got extremely lucky this time not to get fried by it. Such solar flares often cause long-lived, raging radiation storms, and if such a storm moves in the direction of Earth, it can lead to worldwide blackouts. Before we go deeper into details of that potentially disastrous solar flare, we need to figure out what exactly this solar phenomenon is. Solar flares occur because the magnetic fields in the atmosphere of our star are moving non-stop. When the Sun is approaching its solar maxima, and that's the most active period of its 11-year-long cycle, which is, by the way, exactly what's happening now, its magnetic fields get more and more tangled, making our star look like an enormous ball of tangled rubber bands. They loop around, cross over one another, cut one another off, and then reconnect. Ever seen iron filings sprinkled on a bar magnet? These filings line up along the magnetic lines of force. Like that, the hot plasma on the surface of the Sun is at the mercy of the magnetic lines of force. Sometimes, when the magnetic fields interact with each other, some plasma gets disconnected from the fields, and its particles accelerate to immense speeds and send powerful radiation to space. That's what a solar flare is. Other times, our star throws off massive amounts of matter. Those events are coronal mass ejections, CMEs. Just one CME can contain as much as 20 billion tons of material. If that material were rock, it would create a mountain about 2.75 miles across and almost a half a mile tall. The ejected material often travels at a speed of over 1 million miles per hour. Solar flares and CMEs are the most powerful explosions in the solar system, releasing unimaginable amounts of energy. Solar flares have their own classification according to their strength. The smallest and weakened ones are A and B class. Then there are C and M class solar flares. and the strongest are X-class flares. A number from 1 to 9, and in some cases a larger one, accompanies each letter. That's similar to the Richter scale for earthquakes. A and B-class flares are too weak to affect our planet. As for C-class flares, they may have small, noticeable consequences. M-class flares can cause short radio blackouts at the poles and weak radiation storms that can still harm astronauts. But the most dangerous of them all are X-class flares. These are flares more than 10 times more powerful than X1. That's why the classification of X-class flares can go higher than 9. Now let's get back to that recent solar flare. It was X14 Class 1. Now, we already know that it means it was an extra strong flare. Other large flares astronomers have detected recently include an X12 solar flare that happened on the 20th of May and an X10 flare that occurred on the 17th of July. All of them have come from the backside of the Sun. If we talk of the Earth side of our star, the largest solar flare that has been recorded so far within this solar cycle happened on the 14th of May. It was an X8.7 flare that led to radio blackouts, and a strong geomagnetic storm leading to magnificent auroras all over the world occurred a few days earlier. Powerful coronal mass ejections accompanied this storm. As for the July X-class flare, it was so powerful that it could have ended up tragically for us. Luckily, all that magnetically charged plasma blast that accompanied the flare didn't travel in our direction. If it had, it would have been quite the solar storm. Auroras would have been incredibly impressive and a wee bit terrifying in their magnificence. But at the same time, such a dynamic blast of energetic particles hurtling our way could have caused major technological problems and electrical blackouts, like the event in 1989, which severely harmed Quebec's power grid, or a much earlier catastrophe that still managed to cause a lot of harm to the world. I'm talking about the Carrington event, which occurred in 1859 and was the first documented solar flare affecting our planet. It happened on the 1st of September and was named after Richard Carrington, the solar astronomer who witnessed the flare through his own telescope and sketched the sun's sunspots. According to scientists, that flare was the most powerful documented solar storm over the last 500 years. The Carrington event triggered auroras that were visible as far south as the Caribbean. It led to severe interruptions in telegraph services all over the world, even shocking some telegraph operators and sparking fires after discharges from the lines ignited telegraph paper. Another major solar flare that erupted on the 4th of August, 1972, destroyed long-distance phone communication across a few states, including Illinois. This event even made the American Telephone and Telegraph Company redesign its power system for transatlantic cables. Now let's move to March 1985, when two superpowerful CMEs triggered a geomagnetic storm, which, in turn, set off a power blackout in Canada on the 13th of March. This blackout left around 6 million people without electricity for 9 hours. It is said that the flare disrupted electric power transmission from the Hydro-Quebec generation station and melted a few power transformers in New Jersey. And still, this solar flare was nowhere near the power of the Carrington event. The Bastille Day solar storm took its name from the French national holiday because it occurred on the same day, on the 14th of July in the year 2000. It was an X5 class event that caused some satellites to short-circuit and resulted in radio blackouts. It's still one of the most highly observed solar storm events. From October to November 2003, our star unleashed a series of large solar flares and coronal mass ejections, and they did reach Earth and slam into our atmosphere. Those solar storms, also known as Halloween storms of 2003, caused aircraft to be rerouted, impacted satellite systems, and led to power outages in Sweden. Besides, the Solar and Heliospheric Observatory couldn't fulfill its functions during this solar onslaught. On the 28th of October 2003, the Sun sent a whopper of a solar flare our way. The fire was so powerful it overwhelmed the spacecraft sensor that was measuring it. The sensor topped out at a whopping X28. But later, scientists figure out that the flare had reached a peak strength of about X45. One more thing that made the Halloween storm so scary was that they happen during a time in the solar cycle when solar activity is usually quiet. That's 2 to 3 years after the solar maximum. According to NASA statistics, just 17 powerful flares erupted from our star during that time. The Sun spewed out another X-class solar flare on the 5th of December 2006. It was an X9 class flare that disrupted satellite-to-ground communications and GPS navigational signals for around 10 minutes. That solar storm was so powerful it even damaged the Solar X-ray Imager instrument on the GOES-13 satellite. It sustained damage to several pixels of its detector. In February 2022, SpaceX experienced the terrifying power of our star when a devastating geomagnetic storm destroyed 38 Starlink satellites worth tens of millions of dollars. It happened shortly after they were deployed. Unfortunately, Starlink satellites are especially vulnerable to geomagnetic storms since they're released into extremely low-altitude orbits, between 60 and 120 miles. They also rely on their onboard engines to overcome the drag force and raise themselves to their final altitude of around 350 miles over the surface of our planet. The thing is, during a geomagnetic storm, Earth's atmosphere absorbs energy from the storm, heats up, and extends upwards. It results in a denser thermosphere, which means more drag, and it can be a serious issue for satellites. That's exactly what happened. The batch of newly released Starlink satellites didn't manage to overcome the increased drag and started to fall back, eventually burning up in the atmosphere.
In May 2024, stunning auroras adorning the night sky demonstrated all the power that solar storms emit as radiation. But sometimes, our sun does things that are far more destructive. I'm talking about solar particle events. During these events, blasts of protons coming directly from the surface of the sun can shoot out like giant cosmic searchlights. According to records, an extreme particle event hits Earth every 1,000 years or so. It often causes bad damage to the ozone layer and increases levels of ultraviolet radiation closer to the surface of our planet. Luckily, Earth's magnetic field acts as a powerful protective cocoon for our planet, fending off electrically charged radiation from the sun. In its normal state, this field functions like a ginormous bar magnet, with field lines rising from one pole, looping around the planet, and dropping at the other pole. This pattern is sometimes called an inverted grapefruit. This vertical orientation of the magnetic field at the poles allows some ionizing cosmic radiation to get through the field as far down as the upper atmosphere. There, it interacts with gas molecules and produces the glow we know as auroras. But over time, Earth's protective bubble changes. In the past century, the North Magnetic Pole moved across northern Canada at a speed of about 25 miles per year. Plus, it weakened by more than 6%. Even more shockingly, according to geological records, there have been periods of time as long as centuries and millennia when our planet's magnetic field was super weak or entirely absent. But we'll talk about those tragic times later. It's easy to imagine what our planet would look like without its protective bubble if you look at Mars. The red planet lost its global magnetic field long ago. And once this field disappeared, most of Mars's atmosphere vanished too. In May 2024, a strong solar particle event hit the planet. It disrupted the operation of the Mars Odyssey spacecraft and made radiation levels at the surface of the red planet rise around 30 times higher than what a person receives during a chest X-ray. The sun's outer atmosphere constantly emits a changing stream of electrons and protons, the solar wind. At the same time, the surface of the star also produces bursts of energy, mostly protons, during solar particle events. These bursts of energy have a connection to solar flares, extremely powerful bursts of electromagnetic radiation that can last from minutes to hours. Protons are way heavier than electrons and carry more energy. That's why they can reach lower levels of Earth's atmosphere, exciting gas molecules in the air. These excited molecules emit X-rays invisible to the unaided eye. Dozens and hundreds of relatively weak solar particle events happen during every solar cycle. Now, let's speak about solar cycles for a minute. You see, from a distance, the sun seems to be calm and steady, but if you zoom in, you'll see that its surface is constantly seething and churning. It keeps transforming from a uniform ocean of fire to a chaos of warped plasma and back again in a repeating cycle. Every 11 years or so, the magnetic field of our star gets tangled up. Imagine a ball of tightly wound rubber bands. That's what it looks like at such moments. And then, at one point, it snaps and flips completely, turning the North Pole into the South Pole, and vice versa. Right before this event, the sun steps up its activity. It starts to spit out giant blobs of fiery plasma, emit powerful streams of radiation, and grow planet-sized spots. This period has the name of solar maximum. It's a rather dangerous time for Earth, since it gets regularly hit by solar storms. Such storms have the potential to disrupt communications and damage power infrastructure. Even worse, solar storms can harm astronauts working in space and even make satellites crash into the planet. As the cycle ends, it fades back to the solar minimum, and then a new cycle begins. Anyway, back to our solar particle events. Researchers have found traces of extremely strong solar events happening throughout the history of Earth. And some of them were thousands of times stronger than anything our modern instruments have ever recorded. Such extreme solar particle events happen approximately every few millennia. The most recent one occurred around 993 CE. Beyond the immediate effect they have, solar particle events can kickstart a chain of chemical reactions in the upper atmosphere. And these processes often lead to depletion of ozone, which isn't a good thing. Ozone absorbs harmful solar UV radiation, which can damage not only our eyesight, but also the DNA of living beings. Plus, changing the amounts of ozone in the atmosphere can impact the climate. In a recent study, researchers used large computer models to examine how extreme solar particle events affect Earth. They found out that if a solar proton event arrives during a period of time when our planet's magnetic field is very weak, then ozone damage can last for 6 years, and the level of UV radiation might increase by 25%, boosting solar-induced DNA damage by around 50%. And apparently, this dramatic combination of a weak magnetic field and extreme solar proton events happens quite often. And some researchers believe that it may even explain a few mysterious occurrences in the past of our planet. For example, the most recent period of weak magnetic field started 42,000 years ago and lasted for around 1,000 years. This period included a temporary switch in the North and South poles. Several major evolutionary events happened during that time. For example, the last Neanderthals disappeared in Europe, along with the extinction of marsupial megafauna in Australia. Yeah, sadly, we won't see any giant wombats and giant kangaroos anymore. One more, even bigger evolutionary event might also be linked to Earth's geomagnetic field. Multicellular animals appeared at the end of the Ediacaran period, which started around 635 million years ago, and it occurred after a 26 million year period of extremely weak or even absent magnetic field. The rapid evolution of different groups of animals in the Cambrian explosion, about 539 million years ago, might have also been related to high UV levels and geomagnetism. The simultaneous evolution of hard body shells and eyes in multiple unrelated groups could have been necessary to detect and avoid harmful incoming UV rays. A complete reversal of Earth's geomagnetic poles might have a serious impact on the climate of our planet. Luckily, such flips don't happen overnight. The entire process stretches over thousands of years. Plus, even though the magnetic pole weakens during a pole reversal, it doesn't disappear completely. That's why the magnetosphere continues protecting the planet from cosmic rays and charged solar particles, even though there might be some amount of particulate radiation that will make it to Earth's surface. Our planet's magnetic fields are generated by moving electric charges. If some material allows these charges to easily move in it, it's called a conductor. Metal is a great conductor, and we often use it to transfer electric currents from one place to another. In this case, the electric current's negative charge, called electrons, move through the metal. The current is what generates a magnetic field. Earth's outer core is made of liquid iron and nickel. In other words, there are layers and layers of conducting material inside our planet. Currents of charges are constantly moving throughout the core, and the liquid metal is also moving and circulating there, generating the magnetic field. This magnetic field, in turn, produces something resembling a bubble around the planet. It's called the magnetosphere, and it's located above the uppermost part of the atmosphere. This layer shields and deflects high-energy cosmic ray radiation, which otherwise would be extremely hazardous to people and other forms of life on Earth. The magnetosphere also interacts with the ionosphere, the layer of our planet's atmosphere containing loads of ions and free electrons and capable of reflecting radio waves. The interaction between these two layers and magnetized solar winds is what scientists call space weather. The solar wind is normally mild, and there's no space weather whatsoever. Astronomers have discovered the most massive stellar black hole ever spotted in our home Milky Way galaxy. This newly found space monster is 33 times bigger than the Sun and sits 2,000 light-years away from us. Until recently, the largest stellar black hole found residing in our galaxy has been around 20 times as big as our star in terms of mass. As for the average stellar mass black hole, it's usually about 10 times as hefty as the Sun. Scientists from the European Southern Observatory's Gaia mission spotted the giant black hole after a star started to wobble while orbiting in that area. The black hole got the name of Gaia BH3. The proximity of this space object to Earth makes it the second closest black hole to our planet ever discovered. The nearest one is called Gaia BH1. It's hanging out around 1,560 light-years away from us. This uncomfortably close neighbor has a mass of about 9.6 times that of the Sun. It means that it's way smaller than the newly found black hole. Gaia BH3 is located in the Agila constellation. From Earth, it seems to have the shape of an eagle. Interestingly, astronomers didn't expect to find a high-mass black hole lurking so relatively close to Earth and remaining undetected for so long. Okay, we can probably admit that this stellar black hole is just a small fry compared to supermassive black holes like the one that dominates the center of the Milky Way. I'm talking about Sagittarius A star. This space giant has a mass of 4.2 million times that of the Sun. While a stellar black hole forms when a star collapses, supermassive black giants have their own ways of seeing the light of day. They are usually the result of mergers of progressively larger and larger black holes. We'll talk about that later. First, let's speak a bit more about how stellar black holes form. When stars near the end of their lives, they typically inflate, lose a lot of mass, and cool to form what we know as white dwarfs. Such massive stellar black holes as Gaia BH3 are believed to form when a star doesn't contain heavy elements and loses not so much mass over its lifetime. Such stars are called metal poor. Afterward, instead of cooling into a white dwarf, this star collapses into a black hole. The companion of Gaia BH3 is a very metal poor star. It suggests that the star that collapsed and formed BH3 was metal poor too. Astronomers know of about 50 stellar black holes in the Milky Way. Some black holes are larger than others. You see, the universe is filled with black holes. Some of them are sprinkled randomly throughout galaxies. Others, those giants we know as supermassive black holes, sit at the center of galaxies. While stellar black holes are usually just a few times bigger than the Sun, such space monsters can weigh from 1 million to 1 billion solar masses. But even though they're so much heavier than our star, they're packed into a relatively small area. On a cosmic scale, of course, the size of our solar system or so. Some astronomers think supermassive black holes could form by several stars colliding and collapsing at once, while other experts state that such space objects might have started growing several billion years ago. At first, a small seed appears somewhere out there in space, which then gradually increases in mass to form a black hole. This seed does it through the process of accretion, which basically means gathering more and more matter around itself. Besides the absence of any precise information about the formation of black holes, there's also the black hole information paradox. If a black hole has some mass, and as we know, these spaced objects have a lot of it, then, according to the first law of thermodynamics, it should have a temperature. And according to the second law of thermodynamics, it should also radiate heat. Stephen Hawking showed that black holes are supposed to emit radiation too. These days, this kind of radiation is called Hawking radiation. It should form at the boundary of a black hole, but after proving it, Hawking pointed out a paradox. If a black hole is capable of evaporating, some of the information it contains can be lost forever. The problem is that the information contained in thermal radiation emitted by a black hole gets degraded. It doesn't repeat any information about the matter swallowed by a black hole before. Such an irreversible loss of information contradicts one of the basic principles of quantum mechanics. Physical systems that change over time cannot create or destroy information. It means we must be missing something. Both physicists and mathematicians have tried to come up with different ideas, but they ended with pretty weird results. Some have even claimed that the universe could be holographic. It means that the universe that we know and love is actually the result of some mysterious interactions at the infinitely distant boundary. I told you, black holes are really strange. At the same time, we have definitely found space objects that seem to have the properties of black holes. For example, look at this image of black hole M87 star. It certainly looks like a physical object, but what if black holes don't exist at all? There's an idea that black holes are actually gravastars, a blend of gravity, vacuum, and stars. This theory was first proposed in 2001 by Emil Matola and Pavel O. Mazur. They hypothesized that at one point during the collapse of a large star, intense gravity might transform its matter into a new state. It's similar to what occurs when atoms are cooled to such low energy states that they start acting like a single superatom. When we speak of gravastars, a star might collapse to the point of the event horizon, or the point of no return, and then its matter is transformed into a new state. It exerts enough outward pressure to prevent the star from collapsing into a physics-defying singularity. In gravastars, an ultra-thin, ultra-cold, and ultra-dark indestructible shell surrounds heavily wrapped space-time. This new form of matter turns out to be very durable, but it's also a bit flexible, like a bubble. So anything that's trapped by the intense gravity of a gravastar and smashed into it gets obliterated and then assimilated into the shell of this bizarre space structure. One of the benefits of the gravastar theory is getting away with those messy paradoxes connected with information and singularities. But even though this idea sounds kinda cool, it doesn't explain the phenomena we observe. And we've definitely observed something that looks like black holes. On the other hand, look at this shadow. It isn't caused by the trapping of light in the event horizon. It's a slightly different phenomenon known as the gravitational redshift. It makes light lose energy when it moves through a region with a powerful gravitational field. So, potentially, it could be a gravastar. When the light emitted from the regions close to the alternative objects reaches our telescopes, most of its energy is already lost to the gravitational field, which causes the appearance of this shadow. And still, like with black holes, things get complicated when you add rotation to the equation. Many experts are sure that gravastars would not be able to remain stable during rotation. But wait, it gets even more bizarre. There are suggestions that the insides of gravastars could contain a series of thicker shells. Those are known as nestars, something like a matryoshka doll. Of course, these theories aren't perfect yet. Astronomers still have a lot of work trying to build functioning models. There's also a chance that both black holes and gravastars exist. But then, we've got another problem on our hands. How can we distinguish between the two? Some theories suggest that these different kinds of space objects should also emit very different gravitational radiation. It could allow us to figure out whether we're looking at a gravastar or a traditional black hole.